In this lesson we're going to look at exam questions based on oblique planes. We're going to look at an ordinary level question and then higher level short questions and then higher level long questions that are asked in this topic. Now we have the 2009 ordinary level exam question. What we're given is a fully completed plan. We're given the auxiliary showing how the oblique plane has cut the pyramid, and then we have to complete the elevation. Now we also, in the second part of this, is to find the true shape of the actual cut piece on the pyramid. So if we look at how we're going to do this question, basically to complete the elevation, it's very simply, we have the 4 points in plan, we just bring up the 4 points to elevation and we draw in the cut section. So that's our elevation finished. Now to do the true shape piece, the easiest method is to actually rabat it around. So if we look at the 3D graphic here, we have the pyramid set up, we have the oblique plane here, this here is our cut piece here. Now we're going to rabat this around so it's folding flat on the ground. So that would give us our true shape of this piece, because we can look straight down on top of it, so we'll see the true shape of it. So what we're going to use is we're going to use HT as a hinge. So HT here is our hinge, and we see it as a point in this view here. So this means that we can use this point here and hinge this whole surface around. So to draw this out, what we're going to do is rotate this around, and then we'll bring down our points onto that line. So this is our first point brought down. So we then bring it down parallel to HT, and then this point brought straight out 90 degrees through HT, because this here is the angle in which it's folding down. So this whole object is folding down 90 degrees through HT here. So that's why we're bringing it down here 90 degrees. Now if we look at a second point, we just rabat a second point, same method, that's 2 points, and then we continue with third and fourth point. And this gives us our true shape of our cut section here. So if we see it done in the 3D graphic, then this is the same method here, using the 3D graphic here, just to explain where all these red lines come from. Here we have higher level short question from 2009. In the question we're given a right cone and there's a point P on the actual cone. First part of the question is locate point P in elevation and draw the projections of a sphere which rests on the horizontal plane and touches point P. So this is a typical solids in contact question. Next part then is determine the traces of a plane which is tangential to the cone and to the sphere. So if we have a look at this first, now we're going to bring up point P up to elevation first of all. So what we'll notice here is in the 3D graphic here, we slice across the cone here. This gives us our circle here. So what we're going to do here is take this slice across here, bring up point P up to here, bring it across, and then bring P up. So this explains why we rotate point P in plan. Now next we have to draw a sphere which touches off of it. Now the easiest way to do that is from the side of the cone, draw a line out at 90 degrees because it's touching on this line here, and then bisect our angle here because the sphere is touching both the ground and the sphere at the same time. That gives us our center point. Now the problem with this is it's in the wrong location. We need to bring it down to plan and then rotate it around in plan until we find it in the correct position. So we're going to bring this point down, rotate it around and draw it in its correct position. Then we'll bring it up so the height doesn't change. So we'll bring up the center point and draw our sphere in our correct position. Now the second part of this question is to draw the tangential plane or oblique plane which touches off both of these. Now because it's touching off both of these, the angle of the oblique plane has to be the same as the cone here, so it's resting up against the side of the cone. So what we do in this case here is we put another cone using the exact same angle over the sphere. Okay, so and what we do here is we draw the plan of this. So now we have the plan of both spheres. Now if we look at the 3D graphic, what we're after doing here is putting in the cone here over the sphere, and then we're going to put in our HT here. So this is our horizontal trace here. So our horizontal trace here in the 3D graphic is shown here. Now we'll take the apex point, which we know is on the oblique plane, bring it up parallel to HT, bring it straight up, bring across, and that finds our vertical trace. So if we look at it now in the 3D graphic, done the same method here, and this here shows how it looks like in the 3D graphic here, how the actual oblique plane is touching off both the cone, so it's sitting up against the side of the cone and touching the sphere. So these here would be the two lines where it's tangential to. So in plan here we've just drawn a line down here, 90 degrees to HT, and that's where the actual plane is tangential to. In this higher level question we have to draw the cut shape when an oblique plane cuts through a hexagonal prism. So what we have to do in this question here is draw the elevation of what it looks like when it's cut, and then determine and indicate in degrees the inclination of the cut surface to the horizontal plane. Okay, so if we look at how we deal with this. Now, first of all, we're going to bring our points from plan up to elevation using our traces. So what we're doing here is bringing this point here up parallel to HT, vertically, and then horizontally across. Now this gives us a point here and a point here, because it's both this point and this point. Now next then we take another 2 points, find them 2 locations, and then the next thing then is find the next 2 locations. Now so what we have here is we have our 6 points, we draw in our surface here, and then we complete the elevation by putting in the dotted lines and heavy lines. So that's the first part of this question here. Now in this question here they want to know what angle this surface makes with the ground. Now this is the exact same thing as saying what angle does the oblique plane make with the ground, because this surface here contains the oblique plane. So our easiest way to show this is construct an auxiliary looking along HT, taking a height line anywhere here, and what we're going to do is from the XY line project it up onto this X1 Y1 line, then mark off our height, and then draw in our oblique plane. Now this gives us our required angle, so this here is our required angle of 44 degrees. Now the other method here that we're doing here is just drawing in, showing our hexagonal prism here drawn in and showing how it contains this as well. Now in this question here we have a road sign. What we're asked first of all to do is to complete the elevation, including the directional arrow, and then determine the true shape of that parallelogram road sign. So we look at how we go about doing this. First of all, remembering that it's a topic of oblique planes, if we look at this method here, we have points here. We can bring up our lines straight up because we have the points in plan, so it's a matter of just bringing them straight up here up to elevation. Then we have the 2 points in the arrow that we can bring up. So with the arrow. Now the only tricky part now is to find these parts here. So there's a couple of methods. the easiest method here is to draw a horizontal line here. Well, it will be horizontal. What it is line 1, 3 is on the ground in plan, so it's a horizontal line in elevation. So if we go parallel to it in plan, it means that it will be a horizontal line in elevation. So we've found this point, we can bring this line across. Now we know that this point here can be brought straight up. That gives us our point here. Now we'll do the same method then for the top line. Bring this line up, and that's our directional arrow found. Now in this question, now to get the true shape, we can use the oblique planes method. So what we're going to do is take as if the surface 0, 1, 3 is an oblique plane. So what we have in the 3D graphic here is we have the horizontal trace drawn in to show where it would be positioned. And what it is, we're going to rub back down this surface then down. So what we're going to do is set up our traces first of all. So our horizontal trace is 1, 3. And then to find the vertical trace, we can bring point 0 up parallel to HT, then bring it straight up then and bring 0 across. That finds our vertical trace. Now what we can do in this question then is rabat this shape around. So using the rabatment method, what we're going to do is rabat each of these points around. So you can see this being done in the 3D graphic here. This is what it's going to look like when we're done with it. So like what we're doing here is we're going to set up this and fold it flat on the ground first of all. So first thing we're going to do here is take a point here anywhere, then from this point go out 90 degrees, rabat this around. This now gives us V1T. So this here is our vertical trace when it's folded flat on the ground. Now what we're going to do is bring our points across onto our vertical trace, rabat them around, and then once we've rabatted around, what we do is draw a line horizontally here. And the reason this is horizontal is, remember this line here is horizontal on the ground. This line here was taken horizontally here. So what it is, if we took it horizontally here, we have to bring it back here horizontally. So we're bringing this back horizontally and then point 1 out 90 degrees. So this here is point O found here. Now we do the same for the center points here. So bring them horizontally, rotate them around, then bring it back horizontally, and then bring out our 2 points then. And then finally we have the base point already found, and that's our true shape of our parallelogram found on the ground. So this is the actual size it is in the question. Now this sample question here, we're going to look at a plan drawn in here and a partial elevation drawn in. So what we have constructed here, this is going to be cut by an oblique plane. So this is HT, which is parallel to the baseline here. Now it's constructed at 50 degrees here, so this will be given to you in the question. So basically what we have to do in this question is now draw what this shape looks like when it's been cut. So this here shows the 3D graphic of what it looks like. So what we have to do in this question here is construct an auxiliary looking along HT, then find our vertical trace. So taking a point on the XY line, going straight up, then from this point here project it up at 90 degrees, mark off our vertical trace. Now what we're going to do is draw our auxiliary. So we're going to draw our auxiliary, bringing up all the points. Now what this shows us now is where our object is being cut. So we can see it being cut here, here and here. Now basically the only line we'll see in plan is this point here, this point here, this point here. So what we'll do is bring these points down. So what we'll notice here, this gives us a point here and here. But what you'll notice then is when we bring down the other points here, it doesn't give us any extra information because they're already here. So what we're going to do now is, this gives us our 2 small lines here. Now we're going to bring up our points here. So when we bring up this point here, bring it across, we get a point here and here. And then our two top points are brought up already because we've already found them. And that's our object constructed. Now it's a matter of drawing in the heavy sections here. Now if we want to look at the true shape of the cut surface, we can do the rabattement method. So this is rabatted around, flat onto the ground, projected down here, parallel to HT, and then bringing our points out. So we've A found, and so on with the rest of the points here. So this here is what the true shape of the cut section is now looking like. Now another sample question. This here giving us a hexagon, and then we look at drawing it up here. So what we have here is a pyramid in the shape of a hexagon, and then another section of a pyramid sloping in the way here. So what we have here is we have a horizontal trace, a vertical trace drawn in, and what we want to show is what the shape looks like when it's being cut. So basically an auxiliary would be the correct method to use here. So we set up our x11, y1 line, then we take a height for our vertical trace, then we construct our elevation. So once we construct our elevation in the auxiliary, this here shows us what's now being cut. Now it's important when you're doing a question like this is that you label everything carefully. The reason for this is so that you can see what lines the vertical trace is cutting through. So where these points here are. So we have a line here, so we need to have this labeled properly. So what you'll notice here is this point 4,2, it's the line 2,3 and the line 3,4. So this is actually 2 points here. Now it's a matter of bringing down each of these points now. So if we look at all these points now located here, so these are points located, but we have to remember some of them are in, there's 2 points here, 2 points here. Now so what we're doing here is bringing down our points. So the first point brought down onto the line 0,6, next line brought down, and this is where we have 2 points here. We have a point on the line 50 and 10. Now we're bringing down this, and again this will give us 2 points on the line 0,4 and the line 0,2. Next we look at this point here. So looking at this is on the line 3,4 and 3,2, and then the final point is down the lower section here on the line 3 here going down to the ground. So what we have is we have the full section now of all these points. We can join them all together in plan. Now we can bring them also up to elevation. Now we've completed in plan, we can complete the elevation and then draw in the rest of the elevation in like this, and then complete the rest of the plan. So this here is what the whole shape looks like. Finally now to do the true shape, very simply we take this, rabat it flat onto the ground using HT as a hinge, and then similar to previous questions here where we rotate down all these points around, and then drawing the true shape of this in plan. So this here is the true shape of that cut surface now using this rabatment method here. Now in this question we have an oblique plane, and then we have a sign resting on top of it. So what we're given here is the arrow here, we have the trace drawn in, and then we have the overall height of the sign marked in here, and it's a matter of just drawing in the elevation here. So what we can do here is bring up our points. Now this here, similar to previous questions where we're bringing these points up parallel to HT, then bringing them up onto the vertical trace and bringing them across. So we have all our points found like this. Now this, our arrow drawn in and our sign completed here. Now the next thing is to find the true shape of this. We're going to do the rabatment method where we fold this on the ground. So the first thing we do is we take a vertical measurement here somewhere. So from this we rotate this around. Next thing then is from this point we go out here at 90 degrees. So this here is brought out 90 degrees. This gives us V1T. Now next thing then is we can start dealing with the sine. So to deal with the sine we need to bring our lines across horizontally and then bring it back, rotate around and then bring it back horizontally here, and it's important that this is brought back horizontally. Now this point here, so it's this point here, this is brought out 90 degrees, so that's our first point found, and then we continue on the process bringing lines across here and so on. So we're bringing lines across here, then bringing them down here at 90 degrees as well. So we continue on with the rest of the points here. So that's our true shape of the arrow. Now the final thing is to get the sine itself. And that's what our sine would look like when it's folded down flat on the ground. Now this here is a higher level question. We're given a stand here for a necklace, and what we're going to use is the oblique planes method. So if we were given the question here, base piece here, then we were drawn grid here, and then we had to set up this base piece here. Now all this information was given to you on the exam paper. Then we had the back piece then. Next then is to draw the elevation then, and what we had here was all of this fairly straightforward, drawing the required grade, and then it's a matter of completing this part here. Next then was lower section here, so this here is the stand at the back. Now next here we had to locate points for a parabola and draw the curve here that represented the necklace here. So again, there was no real difficulty in that, it was a matter of finding these points here, drawing our parabola. Next thing here was a matter of bringing these points up here to elevation here, and what they've done here is use these lines going across here horizontally, so we could draw them across here, and they'd top points here. So we had our parabola drawn in here. Now in this question here then, what we were asked to do was to find the traces. So in the first part of the question you were asked for the traces of that contained this sloping surface here, so you have to draw in the traces that contain this. So what we have in the 3D graphic here, we have the horizontal trace drawn in already. So this here is basically what we were asked for. So how do we locate it? So obviously the horizontal trace is very easy to find. It's just a line extended from the base here where it's hitting the ground, so that's our trace. So that's our horizontal trace, and now what we can do is pick any point that is on this surface. So we're picking a line up from this surface here. We'll bring it up vertically then. So once we bring this up vertically, we bring a line across here. This gives us a point on our vertical trace. So that's our vertical trace found. So that's how we find our traces when we have the surface and we just have to draw in the traces. So obviously if it's hitting the ground, that gives us our horizontal trace. Next thing then is vertical trace, is just take any point here. So we could pick any of these points. So if I say, for instance, I take this point here, go parallel to HT, bring it straight up, then bring this point across, it'll give us a point on the vertical trace also. Now in this question here we also had to find the oblique traces for the oblique plane that contained the stand at the back. So again, we had the horizontal trace. The horizontal trace was on the ground because this surface was intersecting the ground. So what we have here in the 3D graphic is a representation of what this oblique plane at the back looked like. So first trace, very easy to find, it's this red line here. But what we should notice in this question now is that this trace now will be going in the opposite direction, okay, because of the angle at which it's sloping at. So what we'll do then is we have to take another point. So we're taking this point here because we know this is on the new oblique plane. So this is brought up parallel, then brought up vertically. This point is brought across, This gives us our vertical trace here. So that's our vertical trace located in this question here. So that was the full exam question based on this topic here. Now this question here, another higher level question from a previous year. So this was using oblique planes method again. So we were given plan and some of the elevation in this, so we had to construct this section of it here. Then there was a small parabola to draw in here. Now in this question here it was actually really simple because it was just drawn with a compass and plan, and then we had to bring up the points here, bring them up to elevation. Now there are several methods that you could use here. The method shown here is where we take generators here, so these are all parallel lines to the sides in plan, so it was a matter of finding these points here. So what it meant then was, if we were doing this in plan, we're just drawing all these lines here, that gives us all our points. So if we bring up all these blue lines now again in our elevation and draw them all in, that gives us all our points. So that was one method of drawing this. So we have all our points brought in here, and that's the shape, the conic shape drawn in there. Now the next part of the question here is to draw the traces. So they wanted the traces for the oblique plane that rested on this cut surface here. So what we have here is in the 3D graphic showing what they're asking. So first of all, we should know the horizontal trace, very easy to draw in, because obviously if this surface is intersecting the ground, we have 2 points here showing where the horizontal trace is. Next thing then is to find the vertical trace. Take any other point that's on the surface parallel to HT, bring it straight up and bring that point across, and that here is our vertical trace located. Now the next thing in this question here was to find the true angle between the traces. So what we have to do is to draw this here is to fold this down flat onto the ground. So if we fold this flat onto the ground, we'll see the true angle between the traces. Okay, so in order to do this, we take a vertical line here, then rotate that around, and obviously from this point here go out 90 degrees and then draw out, and this is how we find V1 out here, and this here is our angle. So basically what we're doing here is grabbing our oblique plane using HT as a hinge and folding it out flat onto the ground. So that's the true angle on which they were looking for. Now this is a sample question showing a mobile phone holder. Now you've got 2 surfaces here, so we have a surface here that could contain an oblique plane, and then another surface here that contains an oblique plane. So draw the given plan. So we're obviously all the measurements were given, so we just draw the given plan. So this here was the given plan, then construct some of the elevation. So surface A here was an oblique plane, so what we're looking at here is this surface here had an oblique plane. So what we have to do here is methods of constructing that oblique plane. Basically what we're looking at here is, if we take a center point here, line 1, 2, extend that line until it hits into the ground, what it'll help us to do is it'll help us to find where the horizontal trace is. So what we're doing here is this line here extended onto the ground. So if we've extended on the ground, hit XY line here, bring it straight down and extend 1, 2 in plan. This gives us a point on the oblique plane. Now what we should notice here is, because this line here is horizontal to this, here is a horizontal line here and contains the actual plane, that means it's horizontal in elevation. So this angle here tells us that the horizontal plane then has to be parallel to it. Okay, so this is here how we draw this line in here. Okay, because this line is horizontal elevation and it's on the oblique plane, that means that HT has to be parallel to this line. So it's an important piece of information to remember this. Now, next thing then, once we have that constructed, it's a matter of, now this is an alternative method of doing it. What we're doing here is, we're setting up an auxiliary here. And what we're doing here is measuring up 50, that's the height of the back section here. What we're going to do, mark up 10 for the front point here. And what we're doing here is extending on this surface here. And obviously this now here is where HT is. So we're bringing this down here. Now this might be an easier method to understand because of we're looking in an auxiliary, and it's a matter of we're looking at an edge view of the oblique plane here. So this here is our horizontal trace. Now obviously the next thing then is to find the vertical trace. Very simply, bring any point that's on it up parallel to HT, bring it up straight, bring 2 across, that finds us a point on the vertical trace. Next here then is bringing up our points here. So we're going to construct our points up here using the horizontal trace method, bringing up lines parallel to it. Next here then we're going to take sections along the circle here, and this is a really quick method in order to draw this circle here. So that's our curve drawn. Now we have the edge here drawn in. So this here is the base. Now we have an opening here. Now next thing we're going to do is construct up this section here. So we're given a height for this in the question. These points brought up here. So this here is our phone now sloping at the required angle. Now the next thing we're going to do is draw the opening section here. So we've the opening section here that we can draw in heavy. So this is our drawing now more or less complete. So this is it put in heavy here. Now the next part of this question was find the traces for this oblique plane now. So what we notice first of all is this is not touching the ground. It's up in the air here. But what we should know is if we extend on the sides here, run into the ground and then bring them down to the plan here, we'll be able to find it. So basically if we colour it in here in red, make it easier to understand, extend on the side here, bring it down to this here, gives us our horizontal trace. And again, remembering this line here is horizontal, so that means our horizontal trace is going to be parallel to it then. So if your line is horizontal in elevation, whatever angle it's in plan, the horizontal trace is going to be parallel to it. Now next thing then is bring up one of the points that's on this surface and then find the vertical trace. So this here is our vertical trace drawn in. These are questions based on oblique planes. So first of all we're going to look at a few short questions from previous exam papers. So what we have here is a flip chart with a bar graph on it. So what you're asked in this question to do is just complete the actual elevation and then determine the true inclination of the diagonal line AB to the horizontal plane. So basically first of all, the reason these are involved in oblique plane questions is because basically this is what you're looking at. This here sign is an oblique plane. So what we should know from oblique planes is any lines that are horizontal in elevation, they'll be all parallel to one another in plan. So what that helps us in this question to do is if we're bringing lines parallel to the edges here, so to find all these points here, if we bring them parallel to the edges here onto this surface here, find them up here, we can draw them horizontally in elevation. So that's the key on how to draw the graph in this question, and a lot of this is just bringing lines straight up as well. Now also in this question, the second part there is determine the true inclination of the line from B to A, so this diagonal line. So what we have to think of is in here we're looking at this from an angle. So if we imagine B is the top of a cone and this here was a line on the side of the cone all the way down to the base of the cone, the easiest method to find the true angle here is put your compass on point B and rotate A around until a horizontal position here, and then bring this up here, and then you can find your true inclination. And it's just using a rebatment method where we're taking this line, swinging it around till we get it horizontally, and then bringing up to elevation, and then we can see the true inclination it makes to the horizontal plane. Now the next question here, the next short question here, is a more traditional oblique plane question where you're given the traces, you're given some of the elevation and plan completed. What you have to do in this case here is to complete the rest of it. So it's a matter of bringing up our points parallel to HT in plan, bring them onto VT, bringing them across and find them. So the first part of this here is to complete the elevation and plan of the cut prism. Next, when you have that done, is to actually draw in the pictorial. So to sketch in this section here what the actual pictorial of this actually looks like. So what you're doing here is you're just copying what the red lines are here. There's 2 points already done for you. All you have to do here is just do another 2 points here. So you're bringing this point parallel to HT, bringing it up vertically, and then bringing it out parallel again. So this is just testing your understanding of the question. Then the next part of this here is on the orthographic projection on the right hand side, determine the true length of the shortest diagonal line on the cut surface. So again, shortest diagonal, so it's the diagonal going across here. So again, if we're dealing with this, a lot of the time this can be dealt with using one point. The higher point is the top of a cone, the lower point is the base of a cone, rotating it in plan, and then drawing it when it's brought horizontally in plan, drawing the elevation of a new cone. Now the next question here is again a more traditional oblique planes question. What we're given here is a solid being cut by an oblique plane, partial plan is drawn, partial elevation is drawn. So we just need to finish the drawing of what's being cut. So basically in this question here is we have points up here in the auxiliary, we bring them down, we mark them in plan here, we complete the elevation or the plan of this, then we bring the points up to elevation and complete the elevation. Now next part then is get the true shape of the cut surface. So from previous in this lesson, it's been basically the easiest way of doing this is robat this surface down onto a flat line here, bring these lines down parallel to HT, and then bring the points out perpendicular to HT from plan to find our true shape down in this section here. Now this fourth question here, what we have is a solar panel here. First thing you're told is that the solar panel is inclined at 50 degrees to the horizontal plane. So that means that it's sloping at 15 degrees. Now, or 50 degrees, sorry. What we have to do this is find the altitude of the line AC. So we have to find the altitude of this. So we have the base point here. So basically, if we are understanding oblique planes at this stage, the easiest way to find the altitude of it is if we look in here and draw an auxiliary up in this section here, and once we draw an auxiliary we have AB as a point, and then what we do is set up a 50-degree angle. That'll give us the height of CD, thus allows us to find the height here, and then finish the elevation. Really easy, a higher level question. Now the next two questions we've already looked in the video, so these are just how they appeared on the exam paper. So what we've done is we've gone through all these. So what we have here is this is what the exam questions look like. So basically we already know, we just set this all up in plan first, then create our generators here in plan. That's how we find our curve here, and then last piece here is to find the traces, and then the very last point there is find the true angle between the traces. So that's where we're folding down the vertical trace down onto the ground, folding it flat. Next one here we've looked at already. So again, quite an easy question. Set this up in plan first, then bring our points up to elevation, and then next thing then is the two traces. So traces for the front stand and traces for the rear support. Now the final question that we look at here is a question based on oblique planes, and we've actually got a sphere involved in it. So what we have here in the photograph is a golf club. So what we're looking at here is the head of a golf club and a golf ball, and what we're looking here is the actual face of the golf club is inclined at 50 degrees. So if we take, say, maybe a pitching wedge, it's sloped at 50 degrees, and what we're looking then is we need to draw the elevation of it first of all. So all the elevation in this question can be drawn first of all. Now it is a small bit tricky looking at this elevation and all the detail on it, but basically you start off with a baseline 60 first, then you're told that this point here is up 50, so for the top point here up 50. From here we go off at 70 degrees. Now to find this point here, we're not given a height for it, but we know that from this point here it's 75 away, so basically it's a bit of working in reverse. From this point, swing an arc off 75, that'll find us point here. Then we know this line here is up 50, so measure a line up 50, draw a light line across, then rotate our arc up until it hits that line, and that's how we get the face here. Now the next thing then is to locate the sphere here. Looking here, we're told from this point here to over 40, so it's over 40, diameter 50, so over 40 up 25, draw our sphere. So that's the first part of the question, draw the elevation. Next part is determine the vertical and horizontal trace of the oblique plane. So what you're told in this question here is that the golf club, the face of the golf club, is an oblique plane that's inclined at 50 degrees to the horizontal plane. So basically if we think of oblique planes, this line here is our oblique plane, right? This here is our trace. So what we have here is we have a trace here for an oblique plane. So this here is our trace. So if we're looking in along here and we know the auxiliary up here will be inclined at 50 degrees. Basically what we have to do in this question is take a point from here and take another point here, bring it down to plan, mark it off here. So we take this point here, bring this down here, and then create this line at 35 degrees. So this will be our horizontal trace. Next thing then is what we're going to do here is set up an auxiliary. So taking this as HT, mark off our 50 degrees, and then basically work backwards. We'll be able to take a point on our vertical trace then, mark our point on our vertical trace, mark up the way from elevation and draw in our two traces. Now when we've all this done, the next stage of this then is actually draw the plan. So what you're able to do then is once you have the traces drawn in and you have the elevation drawn, you can bring points across onto your vertical trace and bring them down using your traces method. So it's quite an interesting and detailed question testing your knowledge on oblique planes. But that's the questions on this topic of oblique planes.